Yeah.
So Emanuele Vardaci is going to talk about the compound statistical model of the compound nucleus decay. That's a beautiful, famous picture by, yourself. Tell the story, my friend. By Niels Bohr in the Nature paper. So
No, not the Nature paper.
It was in a Nature paper?
No, in a science.
In a science. Oh, right. So Emanuele, actually, before you start, it's our big pleasure that you are here. We've been trying this for many years. Thank you, Emanuele.
Thank you so much. Actually, for me, it's a big honor because I enjoyed very much my time in South Africa most of the time. Actually, I would say every time. And so I'm very happy to be here and to try to also to show what we do, but also to help to be part of a community. And I also have good friends around here, so it will be interesting for me. So the subject of actually, I try to split this subject in 2 lectures. Okay. So now my idea is to speak about 45 minutes. This is a typical lecture size of a class in Italy, but I'm sure it is quite a standard thing. So the subject of statistical model is quite a wide one from the, let's say, from the beginning of quantum mechanics, when the people realized that atomic physics started, with the Rutherford experiment. So the big race was how to study the atomic nucleus. And what was interesting at that time, that it was possible to observe transmutation. So that if we take a target of boron and we bombard this target with alpha, we can observe different kind of particle in the output channel, which is called also the exit channel. But what was interesting at that time is that if we change somehow with some mean, we increase the energy of the projectile, we observe a structure in the energy spectrum of the protons. This was quite a tricky thing because people did not know how to interpret this kind of data, and especially because at that time the most common idea of the structure of the nucleus was the shell model, something we have heard about. And there was no way to explain this data by using shell model. At the beginning I'll go a little bit slower just to introduce the subject. Then obviously I'll try to pick up speed. And so the idea now is to start with some kind of experimental information. Okay? Then we'll try to build little by little the logic of a way to explain this data. Okay, then there are many other cases. In example, protons and aluminum, you observe gamma spectra with a lot of peaks. And you can continue. In some cases, this what is called cross-section, the number of counts of some probe at some angle, start to show even more complex distribution. In example, if we bombard proton with aluminum with protons, and we look again at protons in the exit channel, we observe something which is very interesting. It has very complex shape. But instead, if we only observe gamma in the exit channel, we observe again only one peak, instead of this kind of shape that looks like more a diffraction pattern. So this kind of problem, it was not only typical of aluminum, it came out also with carbon. So when we observe protons in the output channel, once again, we observe this funny shape, and then we increase the energy again of the proton, we don't observe anything.
Excuse me, what is the vertical axis?
Excuse me?
What is the vertical
It's the number
axis?
of counts. Okay, at the moment, we can say how many counts I observe at one angle with respect to the beam. I fix the angles, and I change the energy of the projectile. This is called excitation factor. So every time I fix the position of a detector and I increase the energy of the projectile, whatever I observe at that angle is a number of counts. It's called also the yield of the reaction. This yield, if I keep everything steady and I only change the energy, will be transformed into cross-section. You know that cross-section is a very important quantity because it's directly connected to probability of having some reaction. Now, I'm not going to detail why we use cross-section and we don't use probability, but in principle we can discuss also about this. So this quantity here on the y-axis is proportional to probability. And what we usually use as in nuclear reaction is cross-section. Okay, so this axis is cross-section, which is directly related to how many counts I see in this detector. So if I run this experiment for 1 hour and I change the energy, for one energy I have so many counts. When I start increasing this energy, the number of counts reduce, then go up again and then reduce again, and remain more or less constant when I increase the energy. Is that clear? So, but I can continue. I can take many other experimental data where I can example. This is the case of proton and aluminum. Again, here is the yield, and this is the energy of the protons. If I continue, keep increasing the energy, I observe so many funny things. Many peaks, many valleys, peak and valley, peak and valley. But instead, if I use alpha, I look for alpha particles in the exit channel. I don't observe this up and down, but I will observe peaks. Again, if I only do another kind of reaction, which is exactly the reverse reaction of this one. So in this case, this is proton on aluminum, and the output, the exit channel, is alpha, and the residual nucleus is magnesium 24. Now I can switch around. I can say, okay, I try to bombard alpha particle on magnesium, okay, and then I observe protons in the exit channel. So this reaction is exactly the reverse reaction of 2, in which I switch projectile and target with residues and ejectile. And again, what I see that in the proton spectra, which is here the number of protons detected for some fixed energy, again I observe peaks exactly in the same position where I observe this for the reverse reaction. It's quite an interesting pattern. Then again, if I take alpha on magnesium, okay, so I produce exactly the same, I use exactly the same reaction, but observe again alpha in the output channel. I would call this a kind of elastic reaction, which the entrance channel is exactly the same as the output channel. I again observe these funny shapes. Clearly, this was quite a puzzle because, see, this is more, let's say, a magnifier lens. If I use proton channel, I observe these funny shapes up and down. If I use proton gamma channel, I don't observe these funny shapes, I only have positive peaks. What is so?
When you say you're increasing the energy of the proton, it is the incident energy?
The incident energy, the bombarding energy.
And you observe, and the peaks that are taken, these are for the ground state now?
Yes.
Okay.
But this is something we will discover after. Because at the beginning you don't know what is ground state, you know what is excited state.
Okay.
Another interesting thing that happens is that if we take an example heavy ion reaction, in which, but this can be seen also with light ion, in which we bombard a heavy nucleus with another heavy nucleus, and we look for protons or alpha particle in the exit channel, regardless anything. So we fix our detector in some position, and we look for this kind of particles. Obviously, we need to have some detector that is able to discriminate, to tell us if whatever is the signal is connected to an alpha particle or to a proton. We have also other possibilities. Indeed, we don't observe peaks anymore, but we observe distributions which are continuous distributions. This is in case is the energy of the alpha particle, this is the energy of the protons. Okay? This is not anymore what we call excitation function. Now what do? We fix the bombarding energy, okay, and observe the ejectiles. In the case before, we were actually changing the bombarding energy, increasing the bombarding energy. In this case, we keep the energy fixed at some point, and we look for the energy spectra of this particle. And we can see that if we use this, in this case is tellurium-117. If we change the energy of the projectile, okay, this is in one case, second case, So no matter what is the energy of the projectile, these are three cases, three different energy, the shape of the spectra look more or less the same. So some kind of continuous distribution. How to explain and how to combine the effect we see before and the effect we have now. We can continue if we look for angular distribution. Are you familiar with the concept of angular distribution? In this case, what I do, I fix the entrance channel, I fix the reaction, mass, so mass and charge of the projectile, I fix the energy of the projectile, and I go to look for particle in the direction around the beam. Okay, and then I observe that the number of particles that I observe every angle is not constant, generally, but may have some distribution. In this case, we can see that if we change the angles where we observe the number of particles, and so we get these points, this kind of particle distribute in some interesting way, which is practically symmetrical with respect to 90 degrees. Now, there is a small detail here. This is the angle in the center of mass. We will discuss a little bit later what this really means. But what is important to observe is this distribution of data has a symmetry. So we have seen peaks, we have seen continuous distribution, and we also see angular distribution that show other kind of symmetry. And we can continue. These are other cases. So we can change, and we can look in the literature and find many cases. Not only this, we can, in example, look for two different reactions. This is hydrogen plus aluminum, magnesium on carbon. And if we measure the alpha particles at the same angle in some particular condition of incident energy or bombarding energy, we can observe two spectra and that overlap almost very closely without, just very small differences. So, all of these phenomena can be explained from the concept of compound nucleus. This was a key. It was a real breakthrough in 1936. How all of these phenomena could have been explained with one simple idea. The one simple idea is that the reaction occurs in a very specific way. So we have a particle bombarding a nucleus, and the idea is that the reaction occurs in two different stages. First step, the formation of an intermediate system. This is called a compound nucleus. So the projectile fuses completely with the target, and they produce an intermediate system. Why we call this an intermediate? Intermediate because this system does not live forever. At one point, this system starts to decay. It's unstable, it starts rotating. It may do some kind of thing with what we call today fission or fast fission, but this is more interesting for heavy nuclei. So, and after this production, this fuse system, this system lives a long time. And for what? Why it lives a long time? Because all the energy that I put into the system by bombarding it is distributed in this new system in a hopefully way which we call equally distributed. And we understand why this is important. And we hope that this system, in this long time, will also reach what we call statistical equilibrium or thermodynamical equilibrium. We will understand later what we mean for this. After some time, the hope is that the system will decay. How? By evaporating particles, by emitting particles all around. Okay? And the particle that can be emitted can be of any kind. It can be neutron, proton, gamma, anything we know in principle can be emitted by this nucleus. Eventually, this nucleus also will emit photons, okay, until it will remain not excited, so will be into the ground state, not excited, so no other particle. We will have, first of all, a kind of composite system, which is a kind of equilibrated system. But what is the second step? Second step is the decay. So first, formation, fusing of the two systems. Second is decay. What is the key element? The key element here is called the independence hypothesis. This is the idea. Now, we started by Bohr. And the idea is that the modes of decay of the compound nucleus are independent on the way in which the nucleus will decay. It means that the system, once it is created, it will decay independently on the way in which I created it. So this is called also the decay, typically said, the decay has no memory of the way in which the nucleus was formed. So if I form this nucleus, the same nucleus, with the same example angular momentum, the same excitation energy, same condition, it will decay exactly the same way, no matter how the system was formed. This is a very basic part of this moment. It's also called memoryless decay. And this is an example. One of the reasons the particles are going now everywhere, in principle, if the system does not memory, or does not lose memory of how it was formed, particles should go in a direction which is very similar to the direction of the incident beam. Okay? Because in this way, particles remember the initial velocity. If particles scatter everywhere, it means that they don't remember anymore. No, they say they don't have any quantity that has a memory of the incident energy. I have here a very nice picture that a student of mine made a while ago that tells you how this is going to go. So the system rotates for some time and starts evaporating particles around. This is the main idea. So formation and decay are two independent steps. This opens a whole new possibility for understanding our process. So once you have a compound nucleus, it can evaporate protons and becomes what is called evaporation residue. Obviously, these two steps, formation and decay, are independent beside a few things. An example, conservation law. So we still have to conserve energy, angular momentum, and parity, and many other things. Charge number, mass number, and so on. What is the simple explanation that Bohr gave for this? The most simple thing that all physicists should do. Look for analogy. How people could understand this process? Okay, he invented this idea of this basin where you have billiard balls. Okay, you hit a ball and you throw a ball inside this basin. What will happen? That this ball will start to kick all the other balls and they start to kick each other. So in this way, the initial kinetic energy of this particle is distributed randomly. You cannot predict how all the balls will hit each other. And eventually, after this random distribution, one of these balls will get enough energy to get out. Okay? What we have to suppose? Next time we have to suppose there is elastic collision between these particles. If there is a kind of friction, part of the energy will not come out anymore, but will go into heat, obviously. But this is a very simple scheme to understand that some energy, suppose that in this basin there are no balls. If there are no balls, the ball, this heated ball, will go in and out again, immediately. Instead, before we have a particle coming outside, it will take some time because this particle will hit this through some way we can imagine there is some kind of statistical equilibrium, so all the particles have more or less the same energy, and then whenever some will get a little bit more, it will get out. So the distribution of this energy also includes fluctuations. So we cannot predict what is will be the sequence of collisions, and this is called a kind of stochastic process. Another thing that Bohr did is say, okay, we can look at this phenomenon like the heating of a drop. You know that Bohr was also the inventor, the one who suggested the model, the liquid drop of a nucleus, that the nucleus behaves like a liquid drop, a charged liquid drop. So what he did is, okay, let's hit this ball with some projectile, and the temperature of the system will increase. Obviously, the system will cool down. How? By emitting another particle. And this shows that the temperature is higher, you can see it a little bit, then the temperature is lower, then you can have some kind of radiation like photon, until the temperature is zero. The nucleus the temperature of the nucleus is 0. Okay? So, this also tells us that in principle we can start thinking about a kind of analogy between the emission of a particle from a nucleus with the evaporation of a liquid drop. Okay, this is a science. If you guys don't have this one, I can give it to you. Okay, so now the idea is that the reaction is not a straight reaction, A plus X, that goes in B plus Y, but there is an intermediate stage. So, in this case, the reaction proton plus aluminum has some intermediate nucleus which is formed, which is called the compound nucleus. This compound nucleus has a mass, which is the sum of the mass, has a charge, which is the sum of the charges. So, this will be silicon-28. Then eventually will decay in alpha plus magnesium, which is the output channel we have observed. This reaction usually is written also in this other short way. This is usually the what is called the projectile. This is the target. This is the ejectile, and this is the nucleus, which is the residue. So in general now, the reaction that go through intermediate states have this special different kind of notation. So I'm going very slowly, but I'll try to pick up now. What are the consequences of this hypothesis? Besides writing the reaction in a different way, what can we say more now? In principle, we can say that in principle we can produce nitrogen-14 by combining different projectile and target. And in principle, we don't know why, if possible, it can decay in many other projectiles. These are non-nuclei, so if I sum the mass and the charge, I can always find a split that combined together will give nitrogen-14. And in principle, I also can reverse. I can reverse the output channel before and consider this the input channel. And in principle, I can reverse completely. All of this reaction, in principle, should go through nitrogen-14. And we can think of any sample. We can take neon-20. We can take many combinations of projectile and target and end up in many other combinations as the output channel. All of these combinations concern the mass and the charge of the system. Obviously, the question is, are all of these allowed? Because, you know well in thermodynamics, the first principle tells you that you can conserve the energy. You must conserve the energy. But the second principle tells you that not all the combinations, not all the possibilities that are consistent with the principle, first principle, are indeed allowed. So, this holds here too, because we know well that thermodynamics is probably the strongest background for the physicists. Now, what is some of the consequences? Obviously, if now we create the same compound nucleus in a different ways, we create the same excited compound in the same different way, its decay should not depend on the way in which it was formed. So, if I look at the proton spectrum example in this decay, this proton spectra should have exactly the same shape independently on how I created this nucleus. So, my point is that energy spectra of the residues and of the particles, so residues, I mean ejectile and residue, should overlap, following obviously the law of conservation of the kinematics. Not only this, but the direction of emission of the product should not remember the initial direction of the beam. So there should be signatures of isotropy, so emission should be everywhere, but in principle there can be some privileged direction, some direction which has still a particular meaning. Why is this? Because remember, we need to conserve the angular momentum. And the angular momentum is always considered to be a direction around which something may happen. Okay? So if we observe some anisotropy, this anisotropy should not be related to the fact that we are creating an equilibrated system. Should be related to the fact that this system may have some angular momentum that is conserved. But we'll look for this later. So, what is the other consequence? The other consequence is that if the formation and decay are two independent states, how can we write the probability of the production of this output channel if we have this entrance channel? Well, we know that from probability, I hope you remember this, that if we have two events which are independent, okay, the probability of having that specific combination of events, A and B, is written as the product of the two probabilities. Okay, when two events are independent, then I can write the probability that that event occurs as the product of the two probabilities. Now I can turn this into cross-section, because I said this is the same thing as probability. So I can say that the cross-section of having the product B once the projectile A can be written as the product of two factors. One is the cross-section for the formation. So it means what is the probability to fuse the system times the probability of having that specific output channel. So in this case, the first step is the production. The second event is the decay. If these two events are independent, formation and decay, the cross-section of having that particular output channel is the product of the two. So this is another consequence, not only isotropy, not only the fact that spectral mass overlap, another consequence of the independent hypothesis is that this cross-section must be the product of the two. So this is the probability of compound nucleus decay in channel B. This is the probability of absorbing. This is sometimes also connected to what is the capture cross-section, but we will talk about this later. Now, we can express this probability of decay in many ways. You know that there is something which is called the width of a layer, or the lifetime of the decay for some specific nucleus. And this lifetime is connected to what we call the gamma, which is called also the decay width. This is a consequence of the indetermination principle. I hope you are familiar with this. So if I have an unstable system that survives some time, okay, we can assign to this system a probability of decay, which is 1 over tau. No, this is known formula. So in principle, we can write the probability per unit of time as a quantity which is related to this quantity gamma, which is called the decay width. Okay? In principle now, as we have seen before, this compound system can decay not only in proton, but in principle can decay neon plus this case per the neutron, neutron plus a gamma, fluorine plus a deuterium. So each time that I form a nucleus, it can decay in many ways. So I can assign to each decay way, okay, that I indicate a probability. So I can emit alpha, I can emit a neutron, I can emit a gamma, and so on. And obviously, how can I calculate this probability? By doing this ratio, the ratio of the decay width in a certain channel, divided by the sum of all the possible decay chains. Okay? So, in principle, I can write now the new cross-section by using this ratio over gamma. Okay. This means that if you consider again the hypothesis, the independency hypothesis, if I use another combination of projectile target, this reaction will be now turned in P that goes in B, so the same kind of decay but different kind of formation. This part of the cross-section will also only change in the part that concerns with the formation, because the probability of forming the same nucleus by different channels can change. Why can change? Because you can have different masses, okay, you can have different barrier, Coulomb barrier and so on, but we will see this later on. So the only thing that will change if I change the projectile target is this part of the cross-section. This part will remain exactly the same. The hypothesis is that we form in these two different reactions the same compound nucleus, and we understand why we will, I don't know why, but how it will be possible to form the same compound nucleus by combining different projectile target. Obviously now we can play with the energy, and we can do some working on how the system can decay, this is called the two-body kinematics. So you have a projectile and target, they fuse together, and the system will fall apart, okay, will decay. Now we have to remember that if the system fuses, we have two-body system. This two-body system will move in space, in the laboratory frame, with the velocity of the center of mass. So this decay, okay, if I sit on the compound nucleus, I see all the particles going around me. It's like if I sit on a firework. Okay, if I throw in the sky a firework, I sit on the firework, I see everything going around. And I have to conserve the impulse. The linear momentum must be conserved. So the linear momentum of all the pieces in the firework must be zero. Okay? But instead, if I sit in the system, in the laboratory system, what I see this nucleus moving. Okay? And when I see this system moving, this particle, the 3 and 4, will have some additional velocity. So, and this additional velocity must be summed with vector to the velocity of the two particles that I would see if I would sit on the compound nucleus. So, the two reference frames have a relative velocity between each other. And this is the velocity of the center of mass. Okay? This can be calculated. Remember, to calculate the velocity of the center of mass is the velocity of the projectile divided by the mass of the two. Now, remember, I can write this, but maybe it is not that important. The velocity of the center of mass is the velocity of the projectile times the mass of the projectile mass plus mass 2. And what is important to say is that since this is an isolated system, this velocity does not change. In principle, to write this correctly, I should write also, these are vectors, okay? So, during the reaction, okay, I have the formation of this system, then the system will decay. So in principle, if this is a two-body system, isolated two-body system, this velocity should not change. It never changes. There should be indeed a little change, because now when I calculate the velocity of the system up, if I forget about this before, and I look only this particle, and I measure the velocity of this particle, and I again calculate the velocity of the center of mass, the new velocity of the center of mass is now related to m3, this is times now. This would be the new velocity, okay? And indeed this should be v3 times v4, okay? So this should be the new velocity. Now the point is, in principle this velocity should change a little bit, but indeed it will not change so much. So, but this is a more complex problem, we will not go in detail. What we can say now, that these two velocities indeed don't change very much. The only difference will be in the total masses. Why this will change? Because the mass m3 and mass m4, okay, are not exactly the same if some part of the mass has been converted into energy. Okay? But if we consider this mass, and is not the mass in MeV, but is the number, the mass number, which is the total number of nucleons, okay, these two velocities should be practically the same. So, the velocity of the center mass before, the velocity of the center mass after, should be exactly the same. We can also calculate what is called the Q value of the reaction. And the Q value of the reaction is the sum of the masses before the reaction and the sum of the masses after. And this tells you that indeed the mass have changed if this collision is not elastic collision. If it is elastic collision, then the two energy, the sum of the energy before and after, should be the same. So the Q value should be the same. Okay. When the reaction has a Q value which is different than zero, then some part of the mass has been converted into energy, and so we have something that we call endothermic or endothermic reaction. But this is another point. We can calculate a particular Q value, which is called the fusion Q value, which is the mass of the two projectile and target, and the mass of the compound system. This is also called the Q value for the fusion. another important thing we have to mention here is how we can write the energy of the particle in the laboratory frame. Remember that in this two-body reaction, it's an isolated system, the velocity of the center of mass does not change. The center of mass also carries an energy. So it means that this energy will not change in the reaction. It will be the same before and after. What does it mean for us? It means that that energy is never available for the reaction. So, in principle, we can write the energy of the projectile as the sum of two things. This is true for any kind of two-body reaction. So when we have two billiard balls, two stones, two balls, whatever you think about, this part of the energy, which is called the energy that the center of mass carries with it, is never available for the reaction. So, if I split this energy in two parts, which is called the energy of the center of mass and the energy of the motion around the center of mass, the only energy available is this T0. Okay? I know that I'm taking very far away, but can we measure this Q value? Indeed we can, by using two-body kinematics. We can measure this Q value by measuring the energy of one of the two ejectiles. Okay? If we measure one of this energy, okay, by using the conservation of the mass, charge, and so on, we can indeed evaluate what is the Q value corresponding to a specific breakup in the output channel. Well, I'll go further because otherwise I will not make at all. Now, this energetics, okay, of the compound nucleus formation and decay can be seen also in an energy scale. This is the mass of the compound system, and this is the mass of two fragments, which are the projectile and the target. This is an energy scale that goes up like this. Why the mass of the compound nucleus is down here with respect to the mass of the projectile and target? Because we know that if we combine two nuclei, they weight much less. So it means that if I take 10 protons and 10 neutrons and I weight each one, I put on a scale, okay, and then I weight 10 neutrons and protons where they are all binded together, the weight of this system is much less. The difference is called the binding energy, which is also the energy that I have to give to my fuse system to split it apart. Okay? So the energy of these two guys separated is much higher than this case. So when two systems are fused, when I provide energy to my system, I create a compound system now that has an energy that obviously has a reminder of how much energy I put into the system. And this is only the part, T0, which is related to the motion around the center of mass. So the energy available. So, according to Bohr's hypothesis, I've created a compound nucleus which has this excitation energy. So all the energy available in the entrance channel is given to one compound system. What does it mean? What will happen now? The system is unstable and will decay into fragments. Okay? So the two fragments now will have an energy which is only part of what I gave to the system. Because to create these two masses, I have to take into account the energy that goes into the mass itself. So, if it is the level, okay, that I had before, which is also the entrance channel, if these two masses, the total mass is higher than the two masses before, it means that I have to use some of the energy to create these two masses. So I have lost part of the energy. So some of the excitation energy has been lost for the masses. It can also be that one of these two fragments is excited, is itself a nucleus excited. So they will appear in the output channel with less kinetic energy, because part of this kinetic energy has been used to excite one of these nuclei. Indeed, this is very important to observe that this drop into energy goes into the total kinetic energy of the two fragments. It's shared between the two. It does not go in one or the other. It is should be considered as split by two. Usually, we only look at one particle. Remember, when you look at this two body, both of them move. They must move because they need to conserve the linear momentum in the center of mass. So this energy is split between the two masses. Obviously, we can continue. What is this total energy now for us? This excitation energy is the sum of two pieces. The part that we call T0, the energy we provide in the reaction, and this other part, which is the difference of these two masses, which is also called separation energy. This is the energy I need to provide to this compound nucleus to split it in front M1 and front M2. Now, if I look at a case of nitrogen 14, you can see that I can create different level of nitrogen 14 by combining carbon 12 with deuterium, boron, and helium. And also, the system can decay in cases in which the Q value is negative, because this mass here is larger than the original mass. Or I can even have a system whose energy is much lower than the initial. In this case, the Q value is positive. It means that the two fragments have a bigger kinetic energy than I provided at the beginning. Okay, I can skip this part because this is an example on how to do some part of the calculation. Now, one of the things that is very important is how can we measure, give a model or measure the cross-section for the formation of the composite system. In principle, we can resort to a geometrical model, which is the development, the way of writing the cross-section by using partial waves. This is the scattering theory of partial waves. So we can consider in principle the system classically. Okay, we have our target, this is our projectile. We can calculate what is called the cross-section, the geometrical cross-section, which is practically an area, a circle which is a radius, which is the sum of the two radius. Okay, and we multiply this by pi. This is called the cross-section of this reaction. Okay, obviously, if the cross-section is the geometry is such as this distance is bigger, okay, the two particles obviously will not meet. So at least to have an interaction, the radius of this cross-section should be the sum of the two radiuses. Okay, in principle we can do some geometry, and we can also calculate what is called the angular momentum, the entrance channel angular momentum. This quantity here is called the impact parameter. So if the distance, the impact parameter is the sum of the two radiuses, there is a larger probability that there will be an interaction. Obviously, this is a semi-classical approach, because we know that the shape of the nucleus is not exactly like a sphere, okay? But there is some diffuseness. So this is a semi-classical approximation. Then we can continue, okay, and think that according to what is the distance from the two nucleus, so according to what is the impact parameter, we can have a different angular momentum given to the system. And so this can be, obviously no, imagine we can change this value, we can have different value of the impact parameter. For each different value of the impact parameter, we have a different angular momentum given to the system. So if we continue, we can in principle write the total cross-section as an overlap of many impact parameters. And if we overlap all of these impact parameters, we end up, and we consider maximum possibility for the angular momentum, we end up in a shape like this. So the total cross-section should be something proportional to some maximum angular momentum squared in this way. So, indeed, by using heavy-annual reaction, we know that when we increase the angular momentum, we don't get only fusion of the system. We indeed have many other reactions. So the more angular momentum we give to the system, which means the more energy, remember that here the angular momentum also depends on the wavelength. And this wavelength increases when we reduce the energy, and reduces when we increase the energy. So we not only give angular momentum because we get closer to the nuclei, we give also angular momentum because we increase the mass of the system, we increase the energy of the system. And when we increase this, we have many other, we call this reaction channel that opens, and only for the shortest, no, the smallest angular momentum we have fusion. It means that if we have a head-on collision, we have the highest probability of having a fusion. The more we go far, so we go far from a head-on collision, the probability that to open other channels becomes much higher. Now, one of the questions I wanted to ask you, but maybe we'll mention this before. Are we able to generate a distribution of nuclei with the initial angular momentum given by this distribution? Now, suppose that we really want to make not a real experiment, but a numerical experiment. We need to generate a compound system which has different angular momentum, and the angular momentum has this distribution. Are you familiar with the concept of PDF, probability density function? So if I take a random variable and assign to this random variable a PDF, can I generate a sequence of variables that once I will histogram will give me that PDF? This is done usually with the method which is called Monte Carlo method, which I hope I'll have time to discuss later on. Okay, now, in principle, another thing can happen is that for each wave, for each partial wave, maybe I can have some problem. Not every partial wave will produce a fusion of the system. There might be some phenomena that can indeed bring me to a condition which some angular momentum will not meet fusion. Indeed, see, in these cases, in the overlap, in the passage, no, in going from one phenomenon to another, this distribution is not sharp. I cannot say from this angular momentum I have a fusion, and the next angular momentum I don't have a fusion, I have a fission, I have another phenomenon. Because there can be an overlap between this distribution, between the two or more decay. So it means that sometimes some angular momentum produces a fusion, sometimes produces angular momentum. It's difficult to predict. So this means that I can, in principle, extend the same formula that I had before by introducing another quantity which is called transmission coefficient that tells me what is the probability to obtain an angular momentum, a fusion, when I have an interaction with that angular momentum. Okay, but we can use, maybe you are familiar with this, a Sharp-Kadov approximation. Indeed, see, this sum goes up to infinity. Okay? But I cannot calculate something that goes to infinity unless it converges to something. Okay? And this will not converge. So I can use an approximation that this angular moment, this transmission coefficient is 1 in the case in which the angular momentum is less than some maximum value that then I can measure somehow, then I can find out if it exists. And this is 0 above. So I can stop this sum to some angular momentum. Now, and I'll stop probably in a few minutes, few seconds probably, because we have to go, but obviously.
You have some
30 seconds. No, I have a lot more. I'm just the beginning. Okay, so what indeed, if we run some kind of model, okay, we can use quantum mechanics in principle, we can find out what is the total. How can I write this by using this simple model, which is partial expansion of the wave function? I can extend this model, okay, I can use this transmission coefficient and obtain the total cross-section for the production and the decay of a nucleon in some channel. If we use this theory, which is called also the theory for isolated resonances, which is very famous because it's due to Bright-Wigner, it is possible to write this cross-section A to B. Again, see, as product of two factors. There is some part which is concerned with the angular momentum. If the system, the target has some angular momentum at the beginning, as the projectile has some, let's say, intrinsic angular momentum, and so on. And this other part is, one part is, as you can see here, is gamma A, and this denominator, times gamma B, which is exactly the one that I saw before, we showed before. So I can write, in principle, this cross-section as the product of two parts. One is called the Breit-Wigner resonance function, which is a Lorentzian. You probably are familiar with this. Times another factor, this factor gamma BB, which is the probability that the system will decay in channel B. And this function is, you know very well, it is a Lorentzian. It is characterized by some average value and some width. So this tells us that when the nucleus is some excited level, in order to excite it to some level, which is E0, okay, I need to provide an energy which is very close to E0. So it means that if I look at this scheme that I had before, if this nucleus has a level here, okay, I can start exciting this level only when I catch an energy T0 that is very close. Before that, I will not be able to excite the system because there are no level here. This is the analog of a resonant circuit. Now, when you have RLC, you have an external driving force like an alternator. Okay, you give some wave. Okay, you can excite this system only if the frequency of the generator is very close to some specific frequency of the system, which is given by special relation. So if this T0 is such that this distance Ex is star, there is a level, I'll be able to form this system. If no level exists at this energy, the system, the fused system cannot be formed. So this is another limitation. It's like the first principle of thermodynamics and the second principle of thermodynamics. So I can provide energy, but if there is no level, I cannot produce anything there. So this is the idea behind this formula. The idea is that if my energy is far, the energy of the beam is very far from this energy with characterizer level, then the probability, which is this curve, or it means this cross section, is very low. Then, if I keep increasing the energy and I emerge, I get close to E0, the probability of formation is very high. And then the same happens if I go very far. Obviously, one question here is, what can we say here? And then we close. What can we say here? Then the whole picture is clear, because clearly these shapes are very similar to these shapes. So it means that every time I change the energy of the incident particle, I'm getting close to some excited level of the compound system. And the cross-section increases. And the demonstration of this is that if I make the same composite system, which is in this case silicon-28, by using different reaction, by changing the energy of the proton, and by changing the energy of the alpha, I create exactly the same compound system. Why is it the same exact system? Because the energy of the particle that I need, okay, it is exactly, shows a peak exactly in the same place. So it means that here I'm producing one excited level, here I'm producing the same excited level, but in two different ways. The same is excited level of the same compound nucleus in different ways. So the picture of a compound nucleus and the picture of the Breit-Wigner resonances, okay, gives an exact idea that we are producing exactly the same compound system in exactly the same levels in two different entrance channels. So the demonstration of one of the most important demonstrations of the concept of the compound system and of the independence hypothesis is exactly in this shape of these resonances, being exactly in the same place. So I produce the same compound nucleus in two different ways. Now, let me do this, otherwise the lecture will be will not have. Why do I observe this? Why I observe here a Breit-Wigner and I don't observe a Breit-Wigner here? Am I populating in this case the same compound nucleus? Because proton plus aluminum is silicon-28. In this case, again, I have proton plus aluminum, silicon-28. But the decay is gamma. So here I produce again aluminum. Here I have silicon, which is decayed. No? Since will only emit gamma, will not emit particles, so the evaporation rate, the residue here, will still be silicon-28. So it will be exactly the same as the compound nucleus. Why I observe this? In this case, in which I have again proton, in this case, gamma. And this is the same for this kind of reaction. Every time I pp prime, I don't have any more resonances like a sharp, bright beam, but I have this diffraction pattern. Why this is that? This is for a very simple reason. See, when we do pp prime, we have this possibility. We produce a compound system, and the compound system decays back exactly in the same entrance channel. So I bombard with a proton, and again I get a proton. But beside elastic scattering, I can have a specific level in the nitrogen, 13 in this case, that matches the condition that the system, there are no level here. You have a level here that the system can decay again into the proton channel. This is called shape elastic scattering. So you have the impression that you only have elastic scattering, but indeed the particle has been absorbed and then re-emitted again, because energetically this is possible. There's always a probability that the entrance channel will appear again as output channel. So if this is energetically possible, I cannot distinguish if this proton was diffused elastically or was first absorbed and then re-emitted. Because from the conservation, this energy of this proton should be exactly the same of the energy of this other proton. But I cannot say if it was elastically diffused or absorbed and then re-emitted. So, what is now, how can I justify this from the quantum mechanical point of view? Well, you know that from the scattering theory, you can write the cross-section with a theorem called optical theory. You can write this cross-section as the square module of the amplitude function, which is connected to the wave function by this part. Okay? Well, this amplitude function has all the interactions inside. It has the dynamics, the kinematics, it has everything inside. Now, the point is that when we do this interaction, we have to consider two parts. We have to consider the Coulomb interaction, which is the Rutherford scattering, which I also call the elastic scattering, and the amplitude function, which is connected to a nuclear part. What is the point here? Because now the nuclear part is important because the proton is first absorbed, so nuclear interaction is there, and then re-emitted. So in order to describe these two processes, elastic and absorption and emission, I have to consider two amplitudes, and I have to sum these two. Okay? Now, when I calculate the cross-section, I have to calculate the module, or the sum of the two. And the sum of the two modules, and the module of the sum is not equal to the sum of the two modules. You need to consider interference. So if you calculate the square of two complex numbers, the modules of the sum of the square of two complex numbers is not the sum of the modules. You have to consider interference. This interference term depends on the angle. So, this is a pure quantum mechanical effect. In classical physics, you don't have this part. In quantum mechanics, you have this additional part that produces this pattern. Why produce this pattern only in this case and not in this case? Because in this case, see, we have proton in the electron charge and gamma. In this case, we have proton and proton. This proton, when we measure, we cannot say if it comes from elastic or from absorption. So this proton carries the information of the diffraction pattern. And then if we plot that cross-section by considering both interactions, that is what we get. Sometimes the interference is positive, sometimes the interference is negative. Now, this point can be verified very easily, and this is done in my lab all the time by students. by measuring this angular distribution, by measuring cross-section, and if we use a little tand, but I will discuss this eventually some other time if we have. Well, if we put your detectors at 30 degrees with respect to the beam, at minus 30, 50 degrees, 110, and you detect protons, and you change the energy of the bombarding protons, and you detect again proton, you can measure this diffraction part very nicely. And you can see that if you change the angle in the laboratory system, the pattern changes a lot because the interference there changes with the angle. See, in the back is very nice. In the forward direction is a little bit not very deep, as in this case. Why is not very deep? Because if the particle is emitted in the forward direction, it's less close to the nucleus. Coulomb excitation. It's less close to the nucleus, so the minimal distance is much larger in this case than in this case. So the effect here of the nuclear potential is much stronger. So also the interference is much stronger. So this is one case, like I said, minus 130 degrees. So see, you can write the overlap or Lorentzian curve to obtain this diffraction path. So the idea of a composite system is the main point here. Now, what we'll discuss in the next lecture, what will happen when we increase the energy of the projectile. So we increase T0. We increase. When we increase T0, we have another nice phenomenon. That at the same time, the level density of the composite system increases. This was also described by Bohr. If you take level density of a nucleus, when you increase the excitation energy, the levels start to be much closer, much more stuffed together, and in principle, these resonances should all overlap together. Okay, and in this case, we enter into the statistical regime, which will be the subject. This is a big race. It will be the subject of next lecture tomorrow. Sorry, I'm racing a little bit, but I understand
it's okay. We enjoy it so much. When I went to Dubna, when I met a month ago or so, they told me that people go there for colloquium and they don't leave after 3-4 hours, right? The people start discussing physics. It's not like in the US and we have 45 minutes running away in Canada, you know? Or here, people, students, 45 minutes.
I'm sorry.
Over there is 3-4 hours of discussing after the talk.
But so questions tomorrow. Or I don't know.
Any questions? You have any questions? Of course. No, we have time. We have 3-4 hours.
For me, it's not a problem.
We're using the Russian system here. Yes. So, any questions?
Okay.
They are too hungry.
The cause of this pattern is because of diffraction, but why? Could you explain us why it's destructive, a destructive interaction at the beginning and a constructive interference afterwards? So it's all the time like that?
Yes.
So could you explain us why?
It's all time like this because, well, it's a good point, but let's see if I can. I have to go a little bit of detail here now. The point is that if you want to write the amplitude, okay, of the cross section, in order to, let me go back a little bit. Okay. See, in order, suppose you have an isolated resonance in which there is no elastic scattering. This cross section should be the Breite-Wigner shape. Okay. So it means you have to provide a formula for the amplitude, that once you build the module, it becomes like a Breite-Wigner. Okay. And this is a kind of parametric problem because, in principle, in order to have a Breite-Wigner, I have to do something a little bit more complex, which is correlated to a quantity which is called phase shift. Probably you guys know this. It's a much more elaborated system. The idea is that when you, I think I'm trying to give an interpretation of this. So see, this sum is many terms, and it has, it can have parity terms, let's say, these are Legendre polynomial, okay? And you know the Legendre polynomial, the even order are even function. The odd order are how do you call it? Odd functions, okay? So in this formula, you see you also have L, which is the angular momentum. So when you create a nucleus, you must also conserve the angular momentum. So it means that not all of this angular momentum go into the sum. Clear? So when you produce a compound nucleus with some property, okay, this compound nucleus has some angular momentum, it has some parity, okay, and obviously some excitation energy. So not only you have to match the energy, but also you have to match these quantities, because you have to conserve the angular momentum. So it means that in this formula, if you don't know what is the angular momentum, you start checking. You go by chance. You put angular momentum 0, 1, 2, and so on, okay? Until you provide a shape that is like this. So this shape is obtained only if you match in your sum, you only put the correct phase shift and the correct angular momentum. So this shape, if you add the angular momentum 2, 3, 4 and so on, will change completely. So this shape is exactly the conservation of the angular momentum. So in the case of carbon, this angular momentum is I don't know, is some 1/2 or 2/2, is 3/2, I think. So this effect here is always negative because you are populating exactly the same angular momentum that provides in that sum. Sorry, go back. They provide in that sum only the angular momentum, only the value of L that conserves the angular momentum. So this is a direct effect connected to the conservation of angular momentum. If we add angular momentum, this shape will change. And you may have a situation in which it is reversed. So you have positive and then negative. So the fact that it's exactly always the same shape is connected to the angular momentum conservation, and you are sure you are populating exactly the same nucleus, same level.
So it is also an indication of the kind of transition that you are having.
Absolutely. And also the decay is always the same. So you fuse and then you get the emitted proton, and you are sure that you are producing the same angular momentum, the same nucleus, the same level. Now, if you, in example, one angle would be reversed, obviously there would be some mistake somewhere. Okay, so this is also a cross-check that you are measuring the data correctly. This is an experiment that our students in Naples do at our accelerator. So they start from scratch. They make their own setup. They provide their own detectors. We built. This is the preamplifier. These are the detectors. We design what is the geometry of the detector and so on. They learn how to use our accelerator. Yeah, I don't know if you ever seen an open tandem. These are the two stages of the tandem. Then they can run the beam, and they can get this data. They can also run this model, and they can provide the shape. Okay? So this is a way also to understand how you really calculate cross-section, what is an angular distribution, what is an excitation function, and how you combine the effect to try to reproduce your data. It's a very effective way to learn basic nuclear physics and also quantum mechanics.
Excellent. Any more questions? So,
okay, tomorrow we'll go into the dynamical part. Okay.
But right now, let's go before lunch. Let's go downstairs to have the group photo. All right? Thank you so much, Emanuele and John, for this nice.
You also do.
It was great, Emanuele. It was very good.